Let's look at sets and Venn diagrams. Now, a set is just a collection of objects, but we need some new words and symbols and diagrams to be able to talk sensibly about sets and Venn diagrams. So, in our ordinary life, we try to make sense of the world we live in by classifying a collection of things. For example, in English, we can say a flock of birds, a herd of cattle, a swarm of bees, a colony of ants, that represents a set of something. Now we do a similar thing in mathematics by classifying numbers, geometrical figures, and other things into a collection that we can call a set. Now the objects in these sets are what we call elements of a set. Now let's describe a set. Now a set can be described by listing all its elements. For example, we can have this set here with 1, 3, 5, 7, and 9. This is read as you say set S is a set, or you say S is a set of elements 1, 3, 5, 7, and 9. The 5 elements are separated by commas and they are always listed or enclosed within these curly brackets. Now, a set can also be described by writing the description. For example, this can be written as odd whole numbers less than 10. This is the same as this. Then a set also must be well defined. This means that our description of the elements of that set should be clear and not ambiguous. For example, you cannot say a set of tall people. That is ambiguous. That is not a set. Because people tend to, disagree about what is tall and what. So that is ambiguous. It really has to be well defined for it to be a set. For example, we can say a set of letters of the alphabet. That one is a well defined set. All the letters of the alphabet belong to that set. Now let's look at Venn diagrams. Now, diagrams are very important in mathematics because they are easier to deal with because they help us to see the whole situation at a glance. Now, in most problems involving sets, it's convenient to choose a larger set that contains all the elements in all the sets being considered. This larger set is called the universal set. This universal set is usually given a symbol E. Now, in Venn diagrams, the universal set is mostly symbolized with a large rectangle, and then the other sets are represented by circles within the rectangle. So, for example, if you have this, so this is what we call the universal set. The rectangle is the universal set. Now, if you have another set within here, for example, let it be A, E, O, U. Then here we have B, C, D, F, G, H, B, C, D, F, G, H, K, L, M, N, P, Q, R, S, T, V, W, X, Y, Z. Now, for example, V is a set of vowels, and this set of vowels is within the universal set. Now, the universal set is comprised of elements which are letters of the alphabet. So, the universal set has all letters of the alphabet, while set V is the set of vowels. Now, let's look at equal sets. Now, two sets are said to be equal if they have exactly, mark this word, exactly the same elements. For example, if you have a set of vowels in the alphabet, this is equals to this set here, A, E, O, O. So this set is equals to this set. So these are equal sets. Whereas this set here, set of 1, 2, 3, is not equal to a set of 1, 3, 5. These are totally different. They are not the same because they have different elements. Here we have a 2, whereas here we don't have a 2. Here we have 5, here we do not have 5. So they only share 2 members, which is 1 and 3. So they are not equal sets. Equal sets only are equal if they have exactly the same elements, just like this. This is a set of vowels of the alphabet, and here this is also a set of vowels of the alphabet. Now you must note that the order in which elements are written does not matter. For example, if you say 1, 3, 5, 7, and then this is equals to 3, 7, 1, 5. It's the same. The order does not matter. Also, any repetition of an element is ignored. For example, if you have a set of A, B, A, this is the same as saying A, B. Repeating A does not really change anything. It's still a set of A and B. Now, element of is represented by this symbol here. So you can say 3 is an element of set A. For example, if you have this set here, if you have 1, 2, 3, 4, 5, and this is set A. So you can say 3 is an element of set A. Now, you can say 6 is not an element of set A because it's not among these. So 6 is not an element of set A, while 3 is an element of set A. Now we have what we call finite and infinite sets. Now all the ones we have looked at are all finite sets, meaning that we can list all the elements in those sets. For example, if you say a set of whole numbers between 2000 and 2005, these can be listed. This will be a set of 2001, 2002, 2003, and 2004. Note that we don't include 2000 and we also don't include 2005 because they'll say a set of whole numbers between. You must also be careful with the English that is used. So between 2000, that means it lies between. So it's 2001, 2, 3, and 4. Then, if say whole numbers between 2000 and 3000, these are also can also be found. So here you can have 2001, 2002, 2003, and so on up to 2999. So these are finite sets. Now we have also what we call infinite sets. Now, examples of infinite sets, for example, a set of even numbers. I mean, these are very many. You can't list them all. So you can have 0, 2, 4, 6, 8, and so on and so forth. You can't finish them. So that's infinite. This is an example of an infinite set. Then also a set of numbers greater than, whole numbers greater than 2000. This is also an infinite set because you can't list all the elements. And so on. You can't list all the elements of this set here. So these are examples of infinite sets. Now, if you have a set S which has elements 1, 3, 5, 7, 9, then we can say that the number of elements of set S, which is represented by this symbol here. So this here represents number of elements in that set. This is equals to 1, 2, 3, 4, 5. So this is 5. This is how we represent number of elements of a set. So this is equals to 5. For example, if they've told you T is a set with elements, which has elements of letters of the alphabet. So the number of elements of set T, which is represented by this here, will be equals to 26 because there are 26 letters of the alphabet. So that's how you represent number of elements. Now you have to be careful. This being equals to 5 is not the same as saying S has a member 5. This is different from this. Now for this one here, the number of elements of this set will be 1, although it has only one element, which is 5. So here, the number, this represents number of elements in this set. Here, the number of elements in this set are 5. The number of elements in this set is 1, although that element is 5. So you have to be careful with that also. Now we have what we call an empty set. Now an empty set is represented by this symbol here, like this. This means that that set has no elements at all. So nothing is in the whole universe. So nothing in the whole universe is an element of this empty set here. So this here, so the number of elements in an empty set will be equals to 0. And X can never be an element of the empty set. However, whichever figure you want to put for X, it can never be an element of the empty set. Now we have what we call subsets. A subset or a set is usually a list of things which can be further subdivided. For example, owls are a particular type of bird. So every owl is also a bird. So we express this in the language of sets by saying that sets of owls is a subset of the set of birds. Now a set, say S, is called a subset of set T if and only if every element of S is also an element of T. So this is written as S is a subset, this is how it is represented, is a subset of T. So let's say you have set A being equals to 2, 4, 6. And then you have set B being equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here you can say set A is a subset of set B because all the elements in set A are in set B. Then there are some sets which are not subsets of the other. For example, you cannot say birds, a set of birds is a subset of flying creatures. Here it's like you're implying that all birds fly. So this is not true because, for example, we have an ostrich. An ostrich is a bird, but it cannot fly. Therefore, this set is not. And so that is how we represent not a subset of flying creatures. Now, how do you represent subsets on a Venn diagram? Let's say this is our universal set E, and we have a set T, which has a subset that has 1, 2, and 0. It has 0, 1, 2. Then we have 3, 4, 5. So this set is, let's say, S. So here, set S is a subset of set T because all elements of S are also elements of T, whereas not all elements of T are elements of S. So S is a subset of T. You cannot change it around and say T is a subset of S. This is totally wrong. So it's S is a subset of T. Now let's look at complements of a set. For example, if we have let's say set E is equals to a set of letters. Then we have set V is a set of vowels. Now the complement of set V, which is written as this, complement of set V will be a set of consonants. It's like whatever is not in set V and is in set E, whatever is not in set V but is in set E, that will be the complement of set V. Now for intersection of two sets, let's say if you have set A, and in that set we have singers, and you have set B, which has instrumentalists. Then we can say set A intersection set B would be the singers who also play instruments. So A intersection B will be those people who are both singers and instrumentalists. So that is what we call an intersection of sets. On a Venn diagram, it's represented like this. This is the universal set. You have a set V and another set F. If you have A, E, O, U, here we have D, N, G. So here, V intersection F will be equals to a set of I and O. Now the word and represents or tells us that there is an intersection. That means like values are falling in two sets. So when you hear the word and, just think of intersection. If you have, say, set A is equals to, set A has elements of singers, and you have set B, which has elements of instrumentalists. Now you can say set A union set B, which is represented by this, is equals to a set of musical performers. That is singers, also instrumentalists. So A union B means elements of A belonging, elements belonging to A or B. For example, if you have a Venn diagram like this, and this is set S, this is set T, and here we have A, E, O. Here we have 1, 2, 3, 4, 5. So S union T will be A, E, O, 1, 2, 3, 4, 5. So a union means members that belong to set S or to set T, and you must take note of O. So O means, for example, here, it could mean people who are singers or they are instrumentalists. So that is union. Whenever you see O, that means union. For example, if you have a set A having 0, 2, 4, 6, 8, and then you have a set B which has elements 2, 7, 9. So A union B will be equals to 0, 2, 4, 6, 7, 8, 9. All the elements that belong to A or B. Then A intersection B will be those elements that belong to both set A and set B, which in this case is just 2. Okay, so the number of elements in set A union B is 1, 2, 3, 4, 5, 6, 7. 7. While the number of elements in set A intersection B is equals to 1. Now these two sets S and T can also be called disjoint sets because they don't have any member in common. So they are completely apart. They have no member. They don't share any members. In the next video, we shall look at how to use Venn diagrams to solve problems. We shall also see how to use the Venn diagrams, other sets in probability, then also the number line, then also sets with equations, how we deal with them, sets and functions, and so much more. So kindly subscribe to this channel for more amazing videos because a lot is coming up. Kindly subscribe. If you enjoyed this video, give it a like, comment, share with your friends, and also give the video a thumbs up. Also comment what you would like us to discuss about in the comment section. Thank you. Let's meet in the next video. Bye.